Chapter 6 is about circular motion again. Now, we've already talked about circular motion in terms of acceleration, but we're going to talk about it in terms of mass now. We're going to talk about gravity and satellites as well. Let's start with section 6.1 and talk about the forces in circular motion. We already know that if we have an object that's traveling in a circle, that it has an acceleration that points along the radius. We call that the radial acceleration or the centripetal acceleration. And it's equal to v squared over r. That's the speed squared over the radius. When something's moving in a circle, particularly a circle if we're talking about uniform circular motion or motion at a constant speed, the net force has to point along the acceleration. So when something moves in a circle, the net force is actually the centripetal force. And we get that by just doing mass times the centripetal acceleration, or mass times the radial acceleration. So when something moves in a circle, it's just mv squared over r. I want to be clear, that is a centripetal force. Centripetal means center seeking. Like I say, also we hear it called radial, along the radius, not centrifugal. You've probably heard of centrifugal forces, which isn't even a force. When something's flying around in a circle and you think it wants to go flying off, that's actually its inertia. Everything wants to continue in a straight line. So if this is a toy, and you're swinging it, let's say you're swinging it above your head horizontally, and all of a sudden this string breaks, this toy will go flying off in a straight line. It doesn't go flying off in a straight line because there's a force pulling it in a straight line. There is no centrifugal force. It goes flying off in a straight line because of inertia, because it tends to continue to move in the direction it was moving. And right at this point, the velocity was in that direction. Okay, so these are a centripetal force. The period, we represent period with a capital T. We generally use a lowercase t for time when it can be any time, but the period's a very definite time. It is the time for one complete revolution or cycle. We'll talk about other types of repeating or cyclical motion, but in this case, the period's just a time to go all the way around. If we think about it that way, we can figure out that the speed, or v, would simply equal the circumference over that period. Or the speed is equal to 2 pi r over t. We can substitute that in this formula. Remember, our formula says that our radial acceleration or our centripetal force, whichever we want to talk about, is V squared over R. Well, how would we do that? If I just take all of this and put it in for that, I have to square all of that. It's going to be 2 pi r over t squared. And then since we're dividing by r, I'll put that times 1 over r. And we get that the radial acceleration can be expressed as 4 pi squared r over t squared. Now that's not one I have memorized because I really do understand this concept that I know the speed is the circumference divided by the period, so I can usually just calculate that and put it in here. But this gives you a formula for this speed that is just a little different. If you know the radius and you know the period, you can get the centripetal or the radial acceleration. And again, if we want force, we just have to multiply that by the mass. Let's look at an example. And this example is right out of your textbook. I'm not sure. I think it's example 6.1. Yes, it is example 6.1. And it says we have a toy airplane on a 5-meter string, and it has a mass of 0.50 kilograms. So we have a toy. The length of the string is going to be the radius of our circle because, of course, it moves around on the end of that string. There's our radius. And they tell us in this case that that radius is 5 meters. They also tell us that the period is 4 seconds. And all we're being asked to do in this problem is to find the centripetal force, or the net force that's acting on the plane. If you were to picture drawing a free body diagram, picture the toy. I wish I had a toy on the end. I'm swinging it in a horizontal circle. There's actually 3 forces that are acting on this. The free body diagram looks like this. The weight of the plane is down, and there has to be some force keeping it up. When we swing it around, if it's not falling, that force is what we call the lift force. And finally, we have the tension in the string. When we swing something around, it's the tension in the string. It's that string that keeps it moving in the circle. I'm just going to use a T for, no, I'm going to use an F. If I use a capital T, that looks like period. So we'll just call that F with an S for string. So those are the 3 forces. Now the weight and the lift force are going to cancel each other out. It's moving in a horizontal circle. It's not a vertical circle. It's not rising or falling at all. The net force then is this force in the string. And we want to find out how big that force in that string is. That's the force. Remember, the acceleration points this direction, then the force points that direction. So we're looking for that force. It's going to be a centripetal force. It makes it move in a circle. So it's mv squared over r. I know the mass. I know how to get the speed, and that's usually my first choice rather than use that formula that's already got it all plugged in. Let's just get the speed. The speed is the circumference divided by the period. The radius is 5 The period is 4 seconds. I put that in my calculator and I find out that it's traveling at about 7.854 meters per second. Again, the problem has 3 significant digits, so I'm going to keep an extra one. I don't want to round too early. So my centripetal force, or the force in the string, is the mass, 0.5, times the speed squared. Some people on the test, I think, did not square that. Over the radius. Everything does have 3 significant digits. I didn't write 3 there. But when I put it in the calculator and I round it, that's my answer. Fairly straightforward because we've really already talked about centripetal accelerations or radial accelerations. All we're doing now is to get forces. We have to multiply that acceleration by the mass of the object that's accelerating. And in this case, when we mean accelerating, we're not talking about a change in speed. We're talking about a change in direction that keeps it moving in a circle. Let's do one more, a little different. This is also from the textbook, and in this case, we have a flat track. Now, I'm not sure of how many of you have been to race tracks. A lot of times they're not flat, they're banked, they're slanted, and by banking them, you can actually use the normal force to help keep the car moving in a circle. But for now, we're going to assume this is a flat track. When a car travels and it turns a curve, the force that keeps it moving in a curve is actually static friction. Now that might surprise you. It's fairly obvious that friction is what keeps a car on the road instead of just sliding off. But when you think about it, a car's tires roll forward. So moving forward, you have something called rolling friction. But the car's tires don't slip side to side. That's static friction. Well, if you turn a corner, it's that static friction, it's that keeping the tires from slipping side to side that actually keep you on the road. If static friction fails, or if you're going so fast, that you exceed static friction, if the force on it's greater than static friction, you'll go sliding off in a straight line instead of rounding that curve the way you're trying to. All right, so we want to calculate the maximum speed that a car can travel around a curve with a radius of r and a coefficient of static friction us. So we're going to do this at first in kind of general terms. So we've got, we'll just say that it has a mass of m. The track has a radius of r. There's a coefficient of friction. And this is static friction. And we're going to call that mu s. Right. Think about this. If we look at it from above, the problem looks like this. You've got a circular track. It's got a radius of r. You've got a car that's traveling in that circle that way. That's what it looks like. If we look at a free body diagram, though, for the car, this time we're looking at it more horizontally. The car's weight pushes it down, that's mg. And there's a normal force. That's the road pushing back up against the car. When a car travels around a horizontal track, it's not accelerating up or accelerating down. So vertically, it's kind of at rest. Horizontally, though, it's moving in this circle. The force that keeps it moving towards the center, this would be that centripetal force, happens to be the force of static friction. Static friction provides the centripetal force. So if we want to write an equation, we generally think that the net force is equal to the mass times the acceleration. Well, in this case, the net force is this force of static friction, which of course is mu s times the normal force. And that has to equal m. And then this, of course, the acceleration in this case is v squared over r. Because this is a centripetal acceleration. This is a centripetal force towards the center. So our static friction force, I should have written it like this. Our static friction force is the centripetal force. Static friction is what keeps you moving in a circle. So there's our equation. We can clean it up a little bit. The normal force, remember our free body diagrams tells you, has to equal mg. So the masses are going to actually cancel out. We have mu s mg and the mv squared over r. They want us to solve, and I didn't even say, they want us to find the maximum speed. Well, the maximum speed occurs at mu s. This is the maximum value of static friction, so that's going to give us our maximum speed. If I solve this, I get v squared equals mu s g times the radius, or the maximum speed is the square root So really not that hard. We know that, let's go back through it. The force of static friction is the thing that supplies the centripetal force. The force of static friction is mu s times the normal force. The centripetal force is mass times v squared over r. I just replaced the normal force with mg, and that way we notice it doesn't even depend on the mass of a car. A slow car and a heavy car can go at the exact same speed as long as the coefficient of friction between their tires and the road is the same. Now, if we want to put in a particular example, we can go back and say, let's look at something with some numbers. If we put in some numbers, perhaps we have a coefficient of static friction that is 0.90, and the radius, the curvature of the road is 250 meters. In that case, the maximum speed would be 0.90 US times G, 9.80 times R. That came out to be 47 meters per second. That is pretty fast. That's approximately 105 miles an hour. Horizontal circle problems aren't too difficult. You just need to think, what is the force that's supplying the centripetal force? If it's a friction force, then friction has to equal that centripetal force. If it's the tension in a string, then the force in the string has to equal that centripetal force. We're going to look at a different problem. We're going to move on. And I want to us to consider vertical motion. Now, vertical circular motion is a little different. Picture the toy on the end of the string. Use your imagination. But this time I'm swinging it, and it's swinging in this vertical motion. If you've ever swung a toy on the end of a string, one of the things that you know is if you go too slow, there won't be enough tension in your string, and the toy will fall from the top. Or if you've ever seen motorcycle riders that do stunts, they can ride through one of those circle loop-de-loop things as long as they're going fast enough. If they try to go too slow, they're not going to make it around the loop-de-loop. So why is that? Well, when we do vertical motion, we have to consider the object's weight. The weight is pulling down at the bottom, but the weight is also pulling down at the top. So let's look at an example of how that works. How does that change things? This is example, I'm going to go ahead and erase that so we have more room. This is out in your book. It's example 6.5. And it involves a Ferris wheel. Now, when something travels around with a Ferris wheel, here's the seats. Let's say you're a passenger and you're sitting in this Ferris wheel. When you're down here at the bottom, your weight is pulling you down, but there's a normal force that's pushing you up towards the center. And in fact, we'll draw a separate free body diagram for what's going on. But in order to be accelerating towards the center of the circle, it makes sense that this normal force is going to have to be more than your weight. Okay. When you're up at the top, your weight points towards the center. Well, if the net force or the centripetal force is towards the center, then probably at the top your normal force might be much smaller. Think about it. At the bottom, the normal force needs to be bigger than your weight. Let me make that a little bit smaller. It needs to be bigger than your weight because we know the net force is towards the center of the circle. But when we're at the top, the normal force needs to be less than your weight because we know the net force has to be towards the center of the circle. Let's suppose in this particular example, we consider we have a 60-kilogram passenger on the Ferris wheel, and the Ferris wheel has a radius of 8 meters, and it has a period of 10.0 seconds. It's traveling at a constant speed, so we know the centripetal acceleration is the same at the bottom as it is at the top. We're not changing that. And they want us to find how much normal force is exerted on the passenger at the bottom and how much normal force is exerted on the passenger at the top. Let's look at the bottom first. Always, ideally, we should draw a free body diagram. We know at the bottom, the net force points up because it's pointing towards the center of the circle. In that case, this gives me this feeling that the normal force minus the weight must equal the centripetal force. Remember, the net force is the same thing as the centripetal force. And we know the net force points up. So the normal force minus the weight must equal the centripetal force. I want to solve for the normal force. I want to see how it varies. You know, usually we think of the normal force being exactly equal to your weight. But in this case, it's not. You can almost imagine riding around a Ferris wheel, how it feels. At the bottom, you feel like it's pushing up on you a lot. But at the top, you really don't feel like the seat is pushing up with you. You almost might feel like it's starting to fall underneath you. So, what do we have? We're looking for the normal force. It will equal the centripetal force, which is mv squared over r plus your weight. 60 kilograms. Oh, I don't know the speed. I've got to stop and find the speed. The speed is the circumference, 2 pi r, over the radius. Whoops. Over the period. Said that wrong. Your speed is the circumference, 2 pi r, divided by the period. When you put that in a calculator, we find out, I didn't write that quantity down. Let's write it down right now. 2 pi times 8 divided by 10 is 5.027. That's how fast, that's our constant speed. Since we've worked that out, I'm going to write it up here. So from now on, we know how fast we're going. Leave myself a little room for a minute. So, 5.027 squared over the radius, that's 8 meters, plus your weight. The normal force has to be enough to be big enough that when you subtract off the weight, you get the net force. So our weight is 60 times 9.80. So 60 times 5.27 squared divided by 8. That came out to be 189.5 newtons plus 60 times 9.8, 588 newtons. All right, let me add that together. I didn't finish the question. So 189.5 plus 588. And I get that at the bottom, the normal force is 778 newtons. Okay. Let's think about what's going to happen at the top now. Remember, if you're watching this, you can always pause it and study and take notes before you go on to the next part. I'm going to leave that free body diagram for just a minute for the bottom. I'll redraw it. You're at the bottom. The normal force is up. The weight is down. But you know that the net force is up. When you're at the top of the roller coaster, the net force is down. Remember, the net force has to point towards the center of the circle. So at the top of the roller coaster, I know the net force is down. The free body diagram still looks like this. I have a normal force, but I must have a much larger weight than the normal. So I think the weight of that person doesn't vary. The weight is always 60 times 9.8, but this normal force certainly can. So when I write this equation, let's write an equation for it now. I get that the net force, or the centripetal force, let's see, is going to be W minus N equals the net force. But remember, the net force is the centrifugal. Notice these two are in the same direction, so I either have to make both of those positive or both of those negative. I made them both positive. The weight minus the normal force equals the net force of the centripetal force. If I rearrange this and solve for N, I get N equals W minus the centripetal force. So 60 times 9.8 minus 60 times mv squared over r. V is 5.027 squared over r. This was 588, I think. Yep. The centripetal force, we already calculated it out once, was 189.5. So at the top, our normal force, 588 minus 189.5, is only 399 newtons. So you do, at the top, you don't feel the seat pressing up with the same amount of force that you feel it pressing up against you when you're at the bottom. Okay? It's all about drawing those free body diagrams and realizing that your centripetal force points towards the center. So the net force points up here, N minus W has to equal the centripetal force. The centripetal force points down here, W minus N has to equal the centripetal force. Let's do another example. This example, I made it myself. It's not in your book. But basically, let's suppose we have a toy on a string. This toy has a mass of 0.10 kilograms. It's on a string that has a length of 0.50 meters. It's a 50 centimeter string. We want to find the tension in the string at the top and at the bottom. Actually, that's not what we want to find. I'm sorry, I didn't read the question. I want us to find the minimum speed that keeps the toy moving in a circle. Picture looks, and this is a vertical circle, and I should have written down, this is we're spinning it around like this in a vertical circle. We could solve something similar with a horizontal, but I want it to be a vertical circle. Now, we know that the toy is being swung around and it has a radius 0.50, and here's a little mass. But we're really interested about what's going on here at the top and what's going on here at the bottom. Just based on your experience, when you swing a toy in a vertical circle, you don't really have trouble with it coming out of the circle at the bottom. You have trouble that if you go so slow, instead of going around, it'll kind of fall out of the circle. The top is the interesting place. So the free body diagram at the top has the weight pulling down and the tension in the string as your other force. Same thing at the bottom, you have the tori, the weight pulling down and the tension in the spring towards the center. Okay. But the top is the interesting place. Minimum speed occurs when the tension at the top is 0. If the tension at the top is 0, that's the minimum speed that you can have. All right, so let's strictly look at the top. If we look at the top, the weight points down, and the net force, or the centripetal force, is down. The net force of the centripetal force has to point towards the center of the circle. This toy is moving in a circle at a constant speed, but it's a vertical circle. So, in this case, the net force simply equals the weight, or mv squared over r is simply equal to mg. So if we want to keep it moving in a circle, we solve this for v. We get v squared equals rg, or v equals the square root r times g. In this problem, our radius was 0.50 meters. G is 9.8. We'll put that in a calculator. And I get that we get a minimum speed of 2.2 meters per second. As long as we swing it with at least 2.2 meters per second, we'll have enough tension. We won't have any tension at the top, but we'll have a lot of tension at the bottom. In fact, if we want to, that's our next question. Let's assume we swing it with a speed of 2.2 meters per second. Let's see if we can find, we know the tension at the top will be 0, because that's how we set it up, where the net force at the top was just equal to the weight, and that was 0. But let's see if we can calculate how much tension is in the string at the bottom, and then let's see if we can calculate the period. Now I need to be careful because I used a capital T on this. Let's go ahead and call that F with a little t, the force of tension. So we're really clear. This is W. All right, we calculated that we're going to use our minimum speed, which was 2.21 meters per second. We'll carry an extra digit. If I draw a free body diagram at the bottom, let's think about what that looks like for the bottom. At the bottom, the net force has to be up because it has to be towards the center. And we know those forces are the force of tension and the weight. Obviously, the tension in the string is going to have to be more than the weight. So I get that the net force, or the centripetal force, has to equal the tension minus the weight. We're solving for the tension. Or the tension has to be equal to the centripetal force plus the weight. That's mv squared over r plus mg. Notice that looks almost identical to what we had when we were finding the normal force at the bottom. The normal force at the bottom of the merry-go-round had to be equal to the centripetal force plus the weight, because at the bottom, that force, that upward force, has to overcome the weight as well. So 0.10, 2.21 squared, 0.50 plus 0.10 times 9.8. And when I plug all of that in, the tension at the bottom Comes out to be 1.96, so to two significant digits, 2.0 newtons. I think in my notes I used 3 throughout the problem, but I decided I just wanted to use 2 in this example. So at the top, the tension in the string was 0, but at the bottom the tension in the string has to be equal to 2 newtons. Notice, if you will, that's exactly double the weight. I believe. Yep, that's double the weight. All right, let's do one more thing with this same problem. Let's see, can we find the period if we're going 2.21 meters per second? What's the period? Well, remember the relationship. The period is the time for one complete revolution. There's a couple of approaches, but one is simply to use the fact that the speed is equal to the circumference over the period, which means that the period is equal to the circumference divided by the speed. So that's 2 pi times 0.50. We're going 2.21 meters per second. This will be in meters. If I put that in my calculator, it comes out to be about 1.4 seconds. Okay, so we've done a couple good examples with horizontal circular motion, things moving on a flat track or just moving horizontally in a circle. And we've done a couple with vertical motion. And the big difference is if we swing it vertically, we have to have a greater tension or normal force or whatever at the bottom because it has to compensate for the weight. But at the top, we could actually get by with a normal force or tension of 0 is if the weight is sufficient to maintain that speed. Okay, that's all for this first part. I will see you with the rest of chapter 6.